Hello and welcome back. In this video, we're working through an example where we'll compute the principal unit normal vector for the helix. So let me quickly remind you about the principal unit normal vector. We can use either of these formulas. If we're arc length parameterized, we can use this first formula here. And then for a general curve, so in most situations, we'll use this formula here when we just have a parameter that we don't know if it corresponds to arc length or not. So it's dt, derivative of the unit tangent vector, divided by the magnitude of the derivative of the unit tangent vector. And let me just remind us geometrically what's going on. Remember these two important facts about the principal unit normal vector is that as I'm moving along this curve, right, my unit tangent vector points in the direction of motion, the unit normal vector points in the direction of turning, right? So if we're accelerating by turning, we will have a positive unit normal vector, and it'll point in, not positive, it's a vector. We'll have a unit normal vector, it'll be non-zero, and it'll point in the direction of the turning. So right at different points along the curve. So notice here we're kind of turning downward along this part, and so my unit normal vector is pointing in that direction. And we can change it as we go. And the other thing to remember is that it's always orthogonal to the unit tangent vector. It's always at 90 degrees to the unit tangent vector. Okay, so let's now compute this unit tangent vector for the helix. Jump down to the task at hand. So again, we're going to work with, just like I did in a previous example video, we're going to work with this general helix. Remember, A is telling us the radius of that circle that appears as the shadow of the helix on the xy plane. That's my A, is that radius. And then B is the vertical velocity of this helix. So some things to right, again, before we actually calculate this, it's a good idea to kind of predict what it's going to be, to have a sort of visual that goes along with it. So what is this unit normal vector going to look like when we keep in mind those two important facts about the unit normal vector? It's always orthogonal to the unit tangent vector, and it points in the direction of turning. So one, we are turning about in a circle, which means we should be pointing to the center of the circle, right? That's our acceleration is going into the center of the circle. And then we think about this z component here. There's no acceleration going on here, right? This is a linear velocity. The velocity is just increasing linearly vertically. So there's no acceleration in the z component. So think about, yeah, what is the unit normal vector going to look like? Is it going to have a z component? Is it going to be constant? What is it going to look like? And then let's actually calculate this. So I'm going to use this formulation for my principal unit normal vector. I'm going to compute dt and then the magnitude of dt. So let's go ahead and first find t. Or rather, we'll first find t, and in order to find t, we need the derivative of this and the magnitude. So v, the derivative of r, will be minus a sine t. Oh, we've done this calculation so many times before. Should be very quick. And then the magnitude of this, magnitude of v is square root a squared sine squared t plus a squared cosine squared t. Oh, I'm going to make sure my scene, switch my scene. Sometimes I forget to switch my scene, and it's not good. I have to redo the video. Yes, it's this. And then, don't forget the plus b squared. We have three terms here. Sine squared plus cosine squared is 1. We just get a squared here, so this is square root of a squared plus b squared. And so my dt then, let's find t. Let's actually find t, and then we'll take a derivative of it. Right, we just go step by step. So what's t? Remember, t is the unit version of my velocity. So divide velocity by the speed. And so we get 1 over square root a squared plus b squared times minus a sine t, a cosine t, and b. So here's my unit tangent vector, t, and then let's go ahead and take a derivative of this with respect to t. What's nice about the speed here, again, we saw this in a previous example with the helix, is that it does have a constant speed, and so that makes this derivative calculation pretty nice. It means I can just pull out the speed as a scalar multiple, a squared plus b squared, and then take the derivative of this. So that's minus a cosine t, minus a sine t, and 0 here. So there's our dt dt. What's the magnitude of this? We're also going to need that, magnitude of dt dt. So again, I can pull out this 1 over square root a squared plus b squared. You might think this is very similar to when we found the curvature of the helix, and it is. All of these pieces are also the pieces for when we're finding the curvature. Right? It involves finding this dt dt and the magnitude of it. And then this is times the square root of, here we'll have a squared cosine squared of t plus a squared sine squared t plus 0 squared. And so that's just a, and we're going to assume a is greater than 0, so square root of a squared is just a, and we get a over square root a squared plus b squared. And so that's magnitude of dt dt. And now we're going to take dt dt and we're going to scale it by 1 over this. So we want to turn this guy dt dt into a unit vector. So we'll divide by its magnitude. So that is, I'm going to multiply by square root of a squared plus b squared divided by a. So let's jump to it. So n of t, I'll remind us it's dt dt over magnitude of dt dt. These are vector quantities. I should have arrows on them. So that's going to be, so flip this, right? 1 over this is square root a squared plus b squared. Or rather, if I'm dividing by it, I'll see the reciprocal. And then times 1 over square root a squared plus b squared. And then times this vector here, minus a cosine t minus a sine t. So that's minus a cosine t minus a sine t, 0. And that gives us, well, these balance out nicely, and then the a balances out nicely with those constants. So what do we get? We get minus cosine t minus sine t. Oh, 0. We still have a z component, it's just 0. And that's my principal unit normal vector. Notice that this is actually the same as the unit vector pointing in the direction of acceleration, and that's because all the acceleration going on for this trajectory about a helix is going into the turning, right? Turning around in the circle. There's no acceleration going vertically because we're just increasing linearly. Right? We have a constant vertical velocity. And so it makes sense that this should be a scalar multiple of the acceleration. And we're actually seeing that. So this should point to the center of that circle. That's the idea. Center of the circle at each level that it's at. So let's go ahead and look at scene 5 here. Let's look at one of these interactive figures that goes along with it. Here's my trajectory along the helix. I can change my a and my b value here. This is a nice one to play around with. Notice that a and b, if I jump back really quickly, my unit normal vector, principal unit normal vector, did not depend on a or b at all. So this will always be the same no matter how wide my radius is and no matter how fast I'm moving upward. It'll always be the same. And so that's kind of telling of what this unit normal vector is really telling us. So the idea, again, is that it's always going to point to the center of the circle. So notice it's parallel to the xy plane, and it's pointing to the very center. So as I move around this, let's change my t value. Notice it's not pointing up at all. Right? When we did our calculation, it had 0 z component. So it's not pointing up at all. And again, that's because we're not turning. We're not accelerating in a vertical direction at all. We're just accelerating by turning around in this circle. That's the only sort of acceleration that's going on, and so that normal vector won't have a z component. It'll just point in the direction of the turning. Notice the unit tangent vector is pointing upward a bit, and that's because we have a vertical velocity. And so there's our geometry for the helix of the unit normal vector together with the unit tangent vector. So tangent vector pointing up a little bit, and unit normal vector has a z component of 0. And of course we can change our a. It's not going to affect what the unit normal vector is. It's still going to point in the direction of the turning, which is to the center of the circle at every point. All right, that is it for this video. Thanks for sticking around. See you next time.